Now, okay, but then many people say, okay, maybe we don't explain the horizon and flatness exactly. Maybe inflation plays part of the role, but there's a deeper mystery to be found, something about the initial conditions yet to be discovered. Yet, inflation has this power to explain a lot of things and to predict a lot of things. And shouldn't we go with that? Isn't that convincing enough to tell us that it's at least part of the story? Well, it would if that were true. But the problem is, those things aren't true either. Okay, so we've also known this as well. And the reason for this is an effect known as eternal inflation. So what is eternal inflation? Well, in the picture that I drew you before of this energy curve, I had a little ball on the hill. It was supposed to represent the value of the field, the value of this inflaton field in space, corresponding to it having a lot of energy, a lot of positive energy that would be driving the inflation. And when I drew that picture, implicit in that was that everywhere over a large volume of space, the field would have precisely that value. But as Max explained, the laws of quantum physics don't allow that. If you try to make something perfectly uniform, in particular, if you try to make energy perfectly uniform, quantum physics forbids that. It'll force there to be fluctuations in energy, which corresponds in this case to fluctuations, for example, in the value of the field. So it won't have exactly the same value everywhere in space. In some places, it'll be further down the hill than others. It'll occupy some distribution. I've tried to represent that distribution with that little badly drawn figure. That's supposed to represent the relative probability of being, there's some peak of it that would be the average value of the field over some volume of space. And you can see some to the right or a little bit ahead, further down the hill. Some to the left are these procrastinating regions which are, a little bit further up the hill. And what you should imagine, therefore, is that what's really happening is that this distribution over space, if you look at a region of space, different regions are heading down the hill at slightly different rates and occasionally being buffeted around by quantum fluctuations. So some will get to the bottom of the hill before others. And those that get to the bottom of the hill you'll form matter and radiation, which will then begin to expand and cool. Other ones will come later, and so they'll end up being hotter than the regions that got there earlier. This is exactly the explanation that Max gave of how we get the hot spots and cold spots that are predicted by inflation to form the hot spots and cold spots of the microwave background. What we see in the microwave background are only tiny deviations from the average. 1 part in 10 to the 4th or 1 part in 10 to the 5th, caused by these quantum fluctuations. So, number one, you can't avoid these quantum fluctuations even if you wanted to, because they're part of quantum physics. And quantum physics, we know, is part of the reality of nature as far as we know. And number two, you don't want to get rid of them because they're the key to getting that prediction, that positive prediction of the cosmic microwave background. But whether you like it or not, something else comes for the ride that I'm going to argue you don't want, which is you also get rare quantum fluctuations. Those ones to the left, those rare quantum fluctuations, which are way behind in the rest, way behind the typical, farther up the hill. They're procrastinating regions in the sense that whereas most of the patch of the universe you begin with might make it down the hill, those at a certain time, those regions might still be on the hill and still inflating, while the rest of the regions have made it down the hill. So they're not just delayed by a little bit, but they're delayed by a lot. There's nothing in quantum physics that we know of that can prevent you from getting those regions, along with the rest. They come for the ride. Now, you might say at first, why do I care about those regions? After all, they're rare. Most of the universe makes it down the hill. When the peak of that distribution makes it down the hill, that little tail to the left contains regions, these rare procrastinating regions, which are unlikely to exist. Not so, because of inflation. You see, those regions are still inflating, while the regions that made it all the way down the hill have stopped. And you have to imagine that inflation is this incredible stretcher of the universe. So within literally a matter of instants, what you thought was a rare, unlikely region of space becomes exponentially most of space. And the region that you thought was typical, the region that made it down the hill, is a tiny little patch or bubble surrounded by that procrastinating regions of space that are continuing to inflate. In other words, when you properly include quantum physics in your thinking, your entire picture of the inflationary universe turns inside out. The regions that end inflation are very atypical. They're a tiny bubble. The regions that haven't yet ended inflation that you thought were rare actually occupy most of the volume. Now, the moment you hear that, you should already begin to wonder, do we get the whole story right? So let's continue and see what happens as a result of that. The regions that are continuing, they're left behind on top of the hill, okay, they're going to have the same situation reoccur again. There's still this hill trying to draw them down. So even though there's a lot of volume, there'll be some regions which are trying to make their way down the hill, in which the field will be changing and slowly making its way down the hill. It'll produce again a patch or a bubble where inflation ends. But still, the procrastinating regions will always win. There'll still be left behind some procrastinating regions, which again, in a matter of instance, occupy even more volume than either of the two bubbles combined. And it will occur again and again and again. So what happens in eternal inflation, when you properly take into account the effects of quantum physics plus inflation, is something quite dramatic. The picture is turned inside out. Most of the universe at any given time is inflating. There are, over time, patches of space which have ended inflating, which contain perhaps hot matter and radiation, which begin to expand and cool. But they occupy an infinitesimal fraction of the entire volume of the universe. And this occurs eternally through time. Now, this by itself might not be a problem. We could just say, okay, the parts of the universe which are inflating are not habitable. The patches which end in inflation would form stars and galaxies which are habitable, and we live inside one of those patches. And I think I would be satisfied with that if it turned out that all the patches had the same physical and cosmic properties. But alas, quantum physics rears its ugly head again. Quantum physics doesn't allow that to happen. Because of the effects of quantum physics, because they're constant, quantum physics always allows fluctuations in this inflaton field that's driving and controlling everything. It's not true that every passage down this curve occurs in the same way. Quantum fluctuations will sometimes form a patch by having the field suddenly jump forward and then make its way downhill, hardly undergoing any inflation at all after that point. Or sometimes it'll jump forward and backwards, or do any other complicated motion. Since the process is eternal, and since quantum physics allows all possibilities, all those possibilities will be explored given enough time. And there's enough time, because inflation is eternal. All of those things will occur. In fact, they will occur more than once. They will occur an infinite number of times. Every possible trajectory of that field down that energy curve will occur an infinite number of times. And depending upon what that trajectory is, you'll have different cosmic properties. So, for example, there will be bubbles, if you've designed the potential appropriately, there will be bubbles which will have regions which are flat and which have simple cosmic microwave background radiation curves that agree with the data just like we see in our own universe. But for every one of those, there will be ones which are not flat, which will be curved. Because those rare quantum fluctuations, those bubbles will end up being curved. For every one of the ones like us, there'll be ones which don't have a microwave background that conforms to the data that you've seen. You'll have, in fact, every conceivable combination of physical and cosmic properties that can occur, will occur, and will occur an infinite number of times. So, whereas you were hoping to explain why the universe has the properties that it does, what you actually did was produce a universe in which literally anything can happen. And what you end up with is not a universe in which the universe is, as you hoped, would everywhere have the properties we observed. You produced a universe which is broken up into bubbles, an infinite number of bubbles, in which every conceivable possibility can occur. In fact, to quote Alan Guth, one of the winners of the Kavli Prize, he's aptly, beautifully describes it as saying, anything that can happen, and it will happen an infinite number of times. So when people talk about the predictions of inflation and talk about it saying that the universe predicts the universe is flat or uniform or any of those things, I just think that's wrong. That's just incorrect. The one thing you can say about inflation that it predicts is that, anything. It predicts a multiverse in which anything can happen and will happen an infinite number of times. And if you ask the question the right way, even the strongest proponents will agree that that is the story.